Here's a final exam for the Calculus and Vectors grade 12 university level course. Now this course is really two courses in one. It's a calculus course and a vectors course. So the final exam, it's basically split into two equal parts. We have 50 marks coming from the calculus part of the course and 50 marks coming from the vectors part of the course. Now all of the questions on this practice exam are questions from past exams that I've given in this course. And if you want to try these questions before watching the video, you can go to jensenmath.ca and get a copy of this blank exam to use it for your studying. Starting with question 1, it says differentiate each of the following with respect to x. Fully simplify your answers and show your work. Let's go ahead and start with part A. In part A, I have 3 different terms that are being added or subtracted, so I can just find the derivative of all 3 of those terms separately and then add or subtract their derivatives. But I noticed that the middle term is going to be a little bit more complicated to differentiate because it has this variable x that's down in the denominator. Before I differentiate it, let me start by rewriting this function in a format that'll make it easier to find the derivative of. This x to the 1 that's in the denominator, I can actually take that term and move it up to the numerator if I change the sign of its exponent. And now to differentiate this function, I can just use the power rule. Y prime, or dy over dx, however you want to denote it, would be equal to the derivative of the first term using the power rule. I take the exponent, multiply it by the coefficient, 3 times 4 is 12. Keep the base of the power as x, and then reduce the exponent by 1, making it 12x squared. Now I'll differentiate the second term. Using the same rule, multiply the exponent -1 by the coefficient of -12, giving me positive 12. Keep the base of the power as x, and then reduce the exponent by 1, making it x to the -2. And then the last term is 71, which is a constant. The derivative of any constant is 0. So I could write plus 0, but that's not necessary. And then to simplify the final answer, we shouldn't have any negative exponents in the final answer. So what I'll do is I'll rewrite this as 12x squared plus 12 over x to the power of positive 2. Right, we can take that power that has the negative exponent, move it down to the denominator, and that makes the exponent become positive. And I'll leave this in standard form as 2 separate terms. We could combine as a single fraction, or we could write it in factored form, but this would be an acceptable simplified final answer. And now let's move on to part B. Part B, I notice I have 2 functions of x being divided, so I'll need to use the quotient rule. And quotient rule says do the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. So my derivative, y prime, would be equal to the derivative of the top, so the derivative of 3x is 3. That gets multiplied by the function in the denominator, minus the derivative of the bottom function, which would be 4x plus 4, multiplied by the top function, 3x. And that's all over the bottom function squared. Now, one important thing to note here is that when I did the derivative of the function in the bottom, I got 4x plus 4. I put that in brackets. And that's so that whole derivative gets multiplied by 3x and not just part of it. And now this expression is the derivative of the original function, but we want to simplify it. The bottom is in factored form, we can leave that, but the numerator, we're going to want to expand it into standard form to see if there's any like terms we can collect. So let me distribute the 3 to all 3 of those terms, and distribute the 3x to both of those terms. And notice I put this product in brackets. That's because we need to subtract that whole product, so I'll have to subtract both of those terms. So on the next line, I'll subtract both of those terms, and then I'll collect all my like terms. When collecting my like terms, I notice I have a 12x minus a 12x. Those will cancel out. And I have a 6x squared minus a 12x squared. That's negative 6x squared. So this whole numerator will simplify to negative 6x squared minus 3. And that's an acceptable simplified final answer. Or from the numerator, we could put it into factored form by common factoring a negative 3. And now let's move on to part C. Part C, I have 2 functions of x that are being multiplied together, so I'm going to have to use the product rule. Product rule says to do the derivative of the first times the second plus the derivative of the second times the first. So using that rule, y prime would be equal to, I have to do the derivative of the first function, which I'll outline in red, and when differentiating that, I actually need chain rule because this is a power of a function. I take the exponent 3, move it down as the coefficient, I keep the base of the power, reduce the exponent by 1, And because the base of the power is not just x, it's a function of x, right? This is a power of a function. I then have to use chain rule, which says multiply this by the derivative of the base of the power. The derivative of x minus 2 is just 1. So I suppose for that derivative, it wasn't necessary, but I'll write that just so you can see where it comes from. So that's the derivative of the first function in the product. That has to be multiplied by the second function in the product, which I'll outline in blue, plus, now I do the derivative of the second function, so the derivative of the blue function. I take the exponent, write it as the coefficient, keep the base of the power, reduce the exponent by 1, but then I have to multiply that by the derivative of the base of the power. The derivative of x squared plus 9 is 2x. And now that has to be multiplied by the first function. So hopefully this color coding helps you see what happened. We did the derivative of the first times the second plus the derivative of the second times the first. And now that is the derivative of the original function, but we want it fully simplified, so we have to get it into either factored form or standard form. Right now it's kind of in between the two because we have a bunch of products, but those products are being added. If we wanted to put it into standard form, because of these powers of 4, there's going to be a lot of multiplying. I think it would be easier if we get it into factored form. So notice this plus sign is separating the two terms from each other. What we want to do is see is there anything in common between those two terms. Well, they both have factors of x minus 2. We can common factor out the one with the smaller exponent, so I'll common factor out an x minus 2 squared from both of the terms. And they both have factors of x squared plus 9. Take out the one with the smaller exponent, so I'll take out an x squared plus 9 cubed. And now I have to divide each of those terms by what I common factored out. So the first term being divided by what I common factored out, the x minus 2 squareds will cancel. This 3 times 1, which is 3, will remain. And x squared plus 9 to the 4 divided by x squared plus 9 cubed is x squared plus 9. Plus, now this second term has to be divided by what I common factored out. This 4 times 2x, which is 8x, will remain. The x squared plus 9 cubed will be divided by x squared plus 9 cubed, so those will cancel out. And x minus 2 cubed divided by x minus 2 squared is x minus 2. Now this is factored form, right? It's a product of 3 factors, but I need to simplify inside of this factor. So I'll distribute the 3 and distribute the 8x. And then collecting like terms in that last factor, I've got 11x squared minus 16x plus 27. And there's the fully simplified derivative. This quadratic factor here does not factor further. And now let's keep going through this question. Let's move on to part D. For this one, we have a radical function. Before differentiating it, it would be easiest if we rewrite it. That square root symbol, we can rewrite that as a rational exponent. A square root can be rewritten as a power of 1 over 2. And then to differentiate this, because what we have is a power of a function, right? This exponent is not just on x, it's on a function of x. I need to use the power of a function rule, which is a version of chain rule that goes like this. To find the derivative y prime, you take the exponent of a half, write it as the coefficient. You keep the base of the power exactly the same, so keep it as 3x plus 4. Reduce the exponent by 1. A half minus 1 is negative a half. But then this has to be multiplied by the derivative of the base of the power, the derivative of the inside function. The derivative of 3x plus 4 is 3. And then we can simplify this final answer, right? We shouldn't have a negative exponent by taking this power that has the negative exponent and moving it down to the denominator with the 2. Or we could convert it back to a radical function, rewrite that 3x plus 4 to the positive a half as the square root of 3x plus 4. All right, we're halfway done the derivatives. Let's go on to part E. This one will be a lot quicker. Here we have an exponential function. We have y equals 2 times 6 to the x. So it's a product, but it's a product of a constant times a function of x. So we can use the constant multiple rule, which says the derivative of this would be equal to that constant, 2, times the derivative of this function of x. And the derivative of 6 to the x is 6 to the x times the natural logarithm of the base of the power 6. And that's it. That's the derivative of that exponential function. Moving on to part F, we now have a trig function. We now have tan x. That tan x is being multiplied by a constant factor of 3. So when doing the derivative, we can leave that constant factor of 3 and multiply that by the derivative of tan x. And the derivative of tan x is secant squared of x. And then plus the derivative of 2, and the derivative of 2 is just 0. So that's it for f. Going on to g, I now have a product of two functions of x, a sine of 2x times e to the 3x. Because they're both functions of x, I'll need to use product rule. I've got my first function and my second function. Product rule says do the derivative of the first times the second plus the derivative of the second times the first. Oh, and this time we have function notation, f of x. So the derivative I'll write as f prime of x equals, I'll do the derivative of the first function, the derivative of sine of 2x. Because the argument is a function of x, I'll need to use chain rule. I'll differentiate the outside function, so the derivative of sine is cos. So it'll become cosine of 2x. Leave the inside function exactly as it is, but then that has to be multiplied by the derivative of the inside function. So the derivative of the argument, the derivative of 2x, is 2. And typically you'll see that constant factor of 2 in front of the trig function. So I'll rewrite that as 2 times cos of 2x. And now that gets multiplied by the second function, plus the derivative of the second function, e to the 3x. Well, the derivative of an exponential, you keep the exponential e to the 3x, times the natural logarithm of the base, so the natural logarithm of e, and the natural logarithm of e is actually just 1, so I don't have to write times 1, so I can get rid of that factor. But once again, because the exponent is a function of x and not just x, I need to use chain rule, which says then multiply this by the derivative of the exponent, and the derivative of 3x is 3. And that has to be multiplied by the first function, sine of 2x. And now there's an acceptable standard form answer, or we could put this into factored form. I know both terms have this power of e to the 3x, so I could common factor that out if I wanted to. So my final answer, f prime of x, if I'm putting it in factored form, I can take out that e to the 3x, and then I'll have to divide both this term and that term by e to the 3x. When dividing the first term by e to the 3x, that cancels, and I just have 2 cos of 2x, plus the second term, when I divide it by e to the 3x, that cancels out, and I get 3 sine of 2x. So there's the factored form final answer. And the last derivative we'll do, once again, is a trig function. For this question, it's going to get complicated because we'll have to use a chain rule within a chain rule. We have a power of a function, which I'll rewrite so you can see more obviously what we have. So I'll rewrite the function f of x. I'll rewrite it as, instead of cos squared of 4x, what that means, it means we have a cos of 4x times another cos of 4x. So I'll write it like this, cos of 4x squared. So we can use the power of a function rule, right? We have an exponent on top of a function of x. So the power of a function rule, which is a version of chain rule, says that we take the exponent, write it as the coefficient. I'll keep the base of the power, keep cos of 4x exactly the same, reduce the exponent by 1, but then I have to multiply by the derivative of the base of the power. And when I do that, I will also need chain rule, because the argument of that trig function is not just x, it's a 4x. So in differentiating cos of 4x, well, the derivative of cosine is negative sine, so I would do negative sine of 4x, but then that has to be multiplied by the derivative of the argument, the innermost function, 4x. The derivative of 4x is 4. And then to simplify this, at the very least, we would have to take these constant factors of 2, negative 1, and 4 and multiply those together to get negative 8. But you may also recognize we have a double angle identity here. If you have 2 times sine of an angle times cosine of the same angle, you could combine those together to write them as sine of 2 times that common angle. So this negative 1 and 4 would stay, making a coefficient of negative 4. But this 2 times cos of 4x times sine of 4x, using a double angle identity, I could rewrite all of that as sine of 2 times the angle of 4x. So 2 times 4x is 8x. These two expressions are equivalent and either would be accepted. So now that you've done all the derivatives, let's move on to the next section where we find the equation of a tangent to a curve at a specific x value. Question 2 says determine the equation of the tangent to this curve when x is negative 2. Let me quickly show you in Desmos what we're trying to find. Here's that f of x function, and we want the equation of the tangent line to this function when x is negative 2. So let me plot a point on this function when x is negative 2, it's at that point negative 2, 4, we want the equation of the line tangent to the function at that point. So there's what that tangent line looks like. We want the equation of that purple line. And to write the equation of a line, we'll do it in slope y-intercept form, in y equals mx plus b form. So we'll need to solve for the slope of the line using the derivative, and also we'll need the y-intercept of that line, which I can see right here is 1 1/3. We'll get that algebraically using the slope and a point that's on the tangent line, which I see is that point right there, negative 2, 4. So let's go ahead and solve for all of that. Let me start by finding the slope of this function at an x value of negative 2. So I'll need to find the derivative, sub in negative 2, and that will tell me the slope of the tangent line. So to get the slope, the first thing I'll do is find the derivative of f of x. I'll find the equation of f prime of x. And this function that we have here is a power of a function, so I'll need to use chain rule. Chain rule will tell me to take that exponent of 2, write it as the coefficient of the power, so I'll start by doing that. I then have to reduce the exponent of the power by 1, so 2 minus 1 is 1. The exponent on this becomes 1. And then I have to multiply this by the derivative of the inside function, so multiply it by the derivative of the base of the power. Well, the base of the power is a quotient of two functions of x, so I'll need to use quotient rule. Quotient rule says do the derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. So following quotient rule, the derivative of the top, 3x, is 3. That gets multiplied by the function in the bottom, minus the derivative of the function in the bottom would just be 1, times the function that's in the top, all over the function that's in the bottom squared. Now I need to find the value of this derivative when x is negative 2. So I can sub negative 2 into this unsimplified version, or I could simplify it a bit first if I wanted to. In the numerator, I have 2 times 3x, which is 6x. And if I distribute and simplify in this last factor, I would have 3x minus 3 minus 3x. And that's all over an x minus 1 times x minus 1 squared. Adding those exponents, I get x minus 1 cubed. Notice these 3x's cancel. And in the numerator, I just have 6x times negative 3, which would be negative 18x. So I'll write my final simplified version there. And now I'll make some room so that I can sub negative 2 into this function to find the slope of the tangent line at an x value of negative 2. So f prime at negative 2, if I sub negative 2 in for x, I would have 36 over negative 27. 9 goes into both of those numbers, so this would simplify to negative 4 over 3, which is going to be the m value, the slope, in my y equals mx plus b formula. I also need a point on the tangent line. Since the tangent line touches the original function f of x at the point when x is negative 2, I can find the coordinates of the point they share just by subbing negative 2 into my f of x function. Evaluating f at negative 2, I get negative 6 over negative 3 squared. That's just 2 squared, which is 4. So the point negative 2, 4 is the point that the tangent line touches the original function at. So that can be the x and the y values that I use in the equation of the tangent line y equals mx plus b. So I'll use 4 for y. M is the slope, which we know is negative 4/3. X was negative 2. And then all we have left to do is solve for the b value, the y-intercept. I have 4 equals 8/3 plus b. To isolate b, I would just subtract this 8/3 to the other side of the equation. So I have 12/3 minus 8/3, which is 4/3. So the b value is 4/3. Meaning the final equation of the tangent line is y equals negative 4/3 x plus 4/3. And now let's go on to questions 3 and 4, where we do some sketching of graphs. Question 3 says, given the graph of f of x, so this graph we have here, let's make it clear this is f of x, sketch a possible graph of f prime of x. Well, remember, f prime of x tells me the instantaneous rate of change, or the slope of the tangent, of this function at all of its x values. Or a simpler way of stating that, the y values of f prime of x tell me the slope of f of x at any given x value. So let's pick out some places where we can very clearly see that the slope of f of x is 0. The slope of f of x is 0 at these 3 points, which means at those corresponding x values, the derivative will have y values of 0, because the y values of the derivative tell us the slope of the original function. And I can see the slope is 0 at all those places because all the tangent lines at those points are horizontal. So at all of those x values, the derivative has a y value of 0. So I can plot points on the x-axis at all of those corresponding x values. Now that I have the x-intercepts of f prime of x, I just need to decide within each interval that I've created, is the function going to be above the x-axis or below the x-axis? And that's going to depend on, is the slope of f of x positive or negative within each interval? So the interval when x is less than -3, so over here, this part of the function. Notice the slope of f of x is positive over that interval. At any point in that interval, if I were to draw a tangent line, it would be going up to the right, which means the derivative, f prime of x, will have positive y values over that same interval. So it's going to have to be above the x-axis. Now between these 2 points on that interval of x values, notice f of x is decreasing. At any point on that interval, if I were to draw a tangent line, it would be going down to the right. So it has a negative slope, meaning f prime of x is going to have negative y values over that interval. So it needs to be below the x-axis. So it would look something like this. And then between these 2 points, over that interval of x values, f of x has a positive slope. It's going up to the right, which means the derivative has to have positive y values over that interval. So it would look something like this. And over the last interval, when x is bigger than 1, notice that f of x continues increasing. So on the interval before 1, it was increasing, but then it went to a slope of 0. And then from that slope of 0, after an x value of 1, it starts increasing again. So it needs to be above the x-axis. It needs to have positive y values for the derivative when x is bigger than 1. So I actually need to change the shape that I just did a little bit. It'll look something like this. Notice at an x value of 1, the y value of the derivative is 0, which means at that x value, there's a horizontal tangent line. It has a slope of 0. Before the x value of 1, the derivative had positive y values, and after, it had positive y values, which means the original function was increasing before and increasing after the x value of 1. And now let's move on to example 4, where we do the same principles, but in reverse. This time, it gives us the graph of f prime of x. And what I want to do is sketch a possible graph of f of x. Since we have the graph of f prime of x, all of the y values that make up this function tell us the slope of the original function. So the slope of the original function when x is -2 is going to be 0, since the y value of the derivative is 0. Which means at -2, there's going to be maybe a local max, maybe a local min, or maybe neither. It'll depend on what happens around that x value of -2. But before -2, the derivative is positive, which means the original function before an x value of -2, it must be increasing. And then between -2 and 2, the derivative is below the x-axis. It has negative y values, which means the original function must have a negative slope over that same interval. So it must be decreasing. So it must look something like this. And then when x is bigger than 2, the derivative has positive y values, which means the original function must have a positive slope, so it must be increasing. Now, because f prime of x was a degree 2 quadratic, we know that f of x must have been a degree 3 polynomial function. So it's not made up of these straight line segments. It's going to be a curved function, but it's going to have those same intervals of increasing and decreasing, and it's going to have a local max at an x value of -2 and a local min at an x value of +2. Now, those local max and min points might be higher or lower than what I have drawn, but they would be local maxes and mins. So let me redraw the function f of x so that it's a curved degree 3 polynomial function. And there's a possible graph of f of x. Whenever f prime of x had positive y values, f of x was increasing. And whenever f prime of x had negative y values, so between -2 and 2, f of x must have been decreasing, right? It would have a negative slope over that interval. And now let's move on to the next question, which is an application of derivatives. It says that Bob is on a diet. His original mass was 102 kilograms. His diet allows him to lose mass exponentially, so his mass is modeled by this function here, where W0 is his original mass, T is time in weeks, and K is a constant. After 3 weeks, his mass is 97 kilograms. Determine the value of k to 5 decimal places. So by subbing into this formula, I know W naught is the initial mass, and it started at 102, and after 3 weeks, so T would be 3, his mass goes down to 97. So W at 3 I could replace with 97, giving me 97 is equal to 102 times E to the K times 3, which I'll write as just 3K. Now we need to solve for K. I'll start by dividing this 102 to the other side, and then I'm looking for what exponent goes on E to get 97 over 102. I can find that exponent, 3K, by doing the natural logarithm of 97 over 102. And this works because the base of the natural logarithm, even though you don't see it, is E. So this is finding out what exponent goes on E to get 97 over 102. And of course, I'll have to isolate K by dividing this 3 to the other side. Or an approximate value, which the question says it wants 5 decimal places for, I can use my calculator, and I get about negative 0.01675. And now I can use that constant K to be able to write an exponential function that models his weight loss. I can say W at T equals the initial amount he started at 102 kilograms times E to the KT, and we now know K. So I'll sub in K. Now the question says, after 10 weeks, at what rate will his mass be changing? If I want to know the rate of change, I need to use the derivative. So I'll need to find the derivative of this function and then sub in 10. To find the derivative, W prime of T, that constant factor of 102 can stay, and multiply that by the derivative of the exponential function. To differentiate that, you always start by keeping the exponential function, multiply that by the natural logarithm of the base of the power, so the natural logarithm of E, which is just 1, so we don't have to write that factor, times the derivative of the function in the exponent of the exponential function. So the derivative of the exponent would just be that constant value of K, negative 0.01675. And now into this function, I want to sub in 10. So W prime at 10 equals, and then I can just use my calculator to find an approximate value. And I get about negative 1.445. That's the rate his mass is changing. So it's going down by 1.445 kilograms every week at that exact moment in time at the 10-week mark. Now moving on to the next question, we're going to look at the curve sketching and optimization questions from the calculus part of the course. The first thing it says this function, which looks like a degree 3 polynomial, has a critical point at negative 2,6. Find the constants b and c. So these b and c values are just constants. If there's a critical point at negative 2,6, I know that negative 2 is a critical number, meaning it will make that degree 3 polynomial, it'll make its derivative be 0. So let me start by finding the derivative of this function. And when I'm doing that, keep in mind I'm treating b and c as constants. So f prime of x would be equal to 3x squared plus 2bx plus 0, right? The derivative of that constant c would be 0. So once again, if negative 2,6 is a critical point, an x value of negative 2 should make this be 0. So let me set it equal to 0, and then sub in negative 2 for x, and then solve for b. When solving this, 3 times 4 is 12, minus 4b, which means 4b is 12, which means b equals 3. So now that I have the value of b, how am I going to get c? Well, I do know a point that is on the function. When x is negative 2, y is 6. So into this equation, I can set f of x, the y value, equal to 6. I can set the x's equal to negative 2, and I can set b equal to 3, and then solve for c. Solving this equation, I have 6 equals negative 8 plus 12 plus c. So 6 equals 4 plus c, which means c is equal to 2. So I have my possible values for b and c. The answers are 3 and 2 respectively. Let's go on to part B that says determine all of the critical points for f of x. So now that I have the values for b and c, I can clearly define my f of x function. Let me find all the critical points for this function. For a degree 3 polynomial function, all of the critical points are going to be the points that have a slope of 0. So I can find those points by finding what x values make the derivative be 0. The derivative, if I differentiate all three terms, I get 3x squared plus 6x plus 0. I know critical points would make this be 0, so I have 0 equals 3x squared plus 6x, and now I just have to solve this. I could solve this by common factoring. I'll take out a 3x from both terms, giving me x plus 2, and then this product would be 0 if either 3x was 0, which would happen if x was 0, or if x plus 2 was 0, which would happen if x was negative 2. So those are my two critical numbers. To get my critical points, I just have to sub each of those x values into the original function to find its corresponding y value. Well, if I sub in 0 for these x's, I'm just left with the constant term of 2. So I know 0, 2 is a critical point. And if I sub negative 2 into this function, I should get 6 according to the information we were given at the start of the question. We could sub it in to make sure. Negative 2 cubed is negative 8, plus 3 times 4, so negative 8 plus 12 is 4, plus 2 is 6. So when x is negative 2, y is 6. So those are the two critical points for this function. And now the question also asks me to classify those critical points using the second derivative test. The second derivative test is going to allow me to figure out if at each of those points there's a local max, a local min, or neither. What I have to do first is, of course, find the equation of the second derivative. So I'll differentiate this first derivative. And then how the second derivative test works is we use this second derivative to check the concavity of the function at the critical numbers 0 and negative 2. So subbing in 0 into my second derivative, I get 6. So the fact that this is positive tells us that at this point, when x is 0, the function must be concave up. And also don't forget, at this point where x is 0, the first derivative is 0, meaning it would have a horizontal tangent, a slope of 0 at that point. So that point must be a local minimum point. If at that point it's both concave up and has a slope of 0, it has to be a local min. So I'll write that down. And now let's test the second point. When x is negative 2, I'll sub negative 2 into my second derivative and check the concavity. If I evaluate this, I get negative 6. The fact that the second derivative is negative tells me that when x is negative 2, the function must be concave down. And if it's concave down and has a slope of 0, it has to be a local maximum point. So there we go. We were able to classify those critical points as either a local max or min using the second derivative test. Let's now move on to question 7. Question 7 says for this function, find its critical points and then use a derivative test to classify them as a local max, a local min, or neither. So to find the critical points, the first thing I'm going to have to do is to find the derivative of this function. And this function, notice, it's a product of two functions of x. It's a power function multiplied by an exponential function. So I'll have to use product rule to find the derivative of this. Y prime would be equal to, based on product rule, the derivative of the first function, the derivative of x cubed is 3x squared, multiply that by the second function, 2 to the power of x, plus the derivative of the second function in the product, the derivative of 2 to the x is 2 to the x, multiplied by the natural logarithm of its base, 2. And that has to be multiplied by the first function, x cubed. So we did derivative of the first times the second plus derivative of the second times the first. And now a critical point would be at an x value that makes this derivative either 0 or undefined. Well, this function is defined for all real values of x, so it can't be undefined, but it could be 0. So I'll set it to 0, and I'll try and solve for what value of x makes it be 0. And if we want to know when something is equal to 0, we should get it into factored form. So looking at these two terms that are separated by the plus sign, what do they have in common? Well, they both have factors of x, common factor out the x squared, and they both have a 2 to the power of x, so I can common factor that out as well. And now I'll divide both of these terms by the x squared 2 to the power of x that I'm common factoring out. And now that it's in factored form, right, it's a product of these three factors, that product would be 0 if any of the factors would be 0. X squared would be 0 if x was 0. 2 to the power of x, that factor can't be 0. That's an exponential function that has a horizontal asymptote at y equals 0. But this last factor could be 0. To figure out when it is 0, let me set up a little equation. if I solve this equation by isolating x, and that has an approximate value of negative 4.328. So that's my second critical number. At those two x values, I know the first derivative is 0. So there might be a local max, local min, or neither. We'll have to classify it using a derivative test. But before I do that, since I want the critical points, I'm going to have to get the y values that correspond to these x values on the original function. So I'll take both of those x's, sub them into the original function for x to get their corresponding y values. And now let's figure out if these points are local extrema using the first derivative test. How the first derivative test works is we use these critical numbers as dividing points, pick test values on either side of those critical numbers, sub them into the first derivative, see if it's positive or negative, and that tells us if the original function is increasing or decreasing, and that will allow us to tell if these points are local max, local min, or neither. So I created the intervals at the top here. On the far left, you always use negative infinity, far right, positive infinity, and then between them, the critical numbers in ascending order. And now I pick test values within each of the three intervals that we've created. In the first interval, between negative infinity and negative 4.3, I'll pick a test value of negative 10. Any number in that interval will be fine. And then I need to take that test value and sub it into my first derivative and see if I get a positive answer or a negative answer. Subbing it in, I would get a negative answer, which tells me the slope of the original function is negative, meaning it must be decreasing. So the original function must be going down to the right. And then within the next interval, between negative 4.3 and 0, I'll pick a test value. I'll pick negative 1. Subbing that test value into the first derivative, I get a positive answer, which means the original function must be increasing. And then within the last interval between 0 and infinity, I'll pick a test value. I'll pick a test value of 2. Subbing that into my first derivative, I again get a positive answer, which means the function continues increasing. And then based on the intervals of increasing and decreasing, we can see that there is only one local extrema. There's a local min at an x value of about negative 4.3. Because before negative 4.3, the function was decreasing, and after it was increasing, so at negative 4.3, it was at a local minimum point. At an x value of 0, which was a critical number, the slope of the function is 0, but because it was increasing before that critical number and increasing again after, it was not a local max or min. So what this function actually looks like based on the intervals of increase and decrease, it must have decreased down to a local min, then increased, then went to a slope of 0, but then continued increasing after that slope of 0. So that's a rough sketch of what that function looked like. And now let's move on to question number 8, where we're given a set of properties for some function f of x, and we have to sketch a possible graph of it. The first bullet point, I noticed, just gives me 3 points that are on the function. When x is negative 2, y is 8. When x is 0, y is 4. And when x is 2, y is 0. So I can plot all of those points on my graph to start. And the next 5 bullet points give me information about both the first and second derivative. It tells me when x is both 2 and negative 2, the first derivative is 0, so the slope of the function is going to be 0 at both 2 and negative 2. And the last 4 bullet points give me intervals over which the first and second derivative are either positive or negative. I notice the dividing points of the intervals are going to be 2, negative 2, and 0. Those are the places that either the first or second derivative are changing signs. So I'll make a number line that has those values as dividing points. Okay, I've got my number line at the top here, but I turn this into a chart so that I can record information about within each interval. What's the sign of the first derivative? What's the sign of the second derivative? And then what does that tell me about the original function f of x? So between negative infinity and negative 2, so when x is less than negative 2, I notice right here when x is less than negative 2, the first derivative is positive. Between negative 2 and 2, the first derivative is negative. So between negative 2 and 2, the first derivative has to be negative. And then when x is bigger than 2, the first derivative is positive. And the sign of the first derivative tells me whether the original function is increasing or decreasing. So when x is less than negative 2, the original function is increasing. Between negative 2 and 2, it's decreasing. And then when x is greater than 2, it goes back to increasing. Now what about the second derivative? The second derivative, when x is less than 0, it's negative, but when x is greater than 0, it's positive. And the sign of the second derivative tells me if the original function is concave up or concave down. So when it's negative, it's concave down, and when it's positive, it's concave up. So within each interval, I should now know what shape the function is going to make. Increasing and concave down looks like this. Decreasing and concave down looks like this. Decreasing and concave up, and then increasing and concave up. So now I just have to take those 4 segments that I just drew in that chart and place them in the correct interval on my graph. So there's a graph that meets all of the criteria of the original question. And just to check, notice it was supposed to have a slope of 0 when x is 2 and negative 2, and at both of those places, there would be a horizontal tangent line indicating a slope of 0. Let's move on to the next question now, which is our optimization problem. A net enclosure for practicing golf shots is open at one end. So this end right here is open. Find the dimensions that will minimize the amount of netting needed and give a volume of 144 meters cubed. Netting is required only on the sides, the top, and the far end, not the bottom or the front. So there's no netting along the ground, and there's no netting along the front. We want to minimize the amount of netting needed, so minimize the surface area, while keeping the volume at 144 meters cubed. That's our constraint. The volume has to be 144, but we're trying to minimize the surface area. Since we're trying to minimize the surface area, we should start by trying to write a surface area formula for this shape. Now, surface area is just equal to the area of all of the sides added together. Keep in mind, there's no net on the front or bottom. Well, if we look at the right side of this shape, it's x by y, so its area is xy. The top is also x by y, and the left side of this shape would also be x by y. So there are 3 sides that are x by y. So to find the surface area of those 3 sides, I could just do 3 multiplied by xy. That's the area of the top, left, and right. We also need the area of the back of this shape. Remember, there is a square at the other end, and its dimensions would be x by x, so its area would be x squared. So I need to add x squared. Now we're interested in minimizing this surface area, but we need to keep the volume at 144 meters cubed. So I'm going to write down my constraint, the volume of this shape, and since it's a square-based prism, I just do the area of the base, which is x times x, and then multiply that by the height of the prism, which is y. So the volume would be x times y, which is x squared y. And I need that volume to be 144. And now what I do with this constraint is I isolate one of the variables, so I'll isolate the y by dividing the x squared to the other side, and I see that y has to be equal to 144 divided by x squared. And what I can do now is take what I know y is equal to and replace it with the y in my surface area formula. And now what we have here is a surface area equation written in terms of only one variable, that variable is x, where this is the surface area of this very specific square-based prism that has a volume of 144. Whatever x is equal to, it will adjust y to keep the volume at 144. And what we want to do is we want to find the minimum value of that function. So let me simplify that function first. 3 times 144 would be 432. And then x divided by x squared, subtract their exponents, it becomes x to the power of negative 1. If I want the minimum value of this function, I need to find its critical numbers. So I'm going to find the derivative. I can just use the power rule for each term. Negative 1 times 432 is negative 432. Keep the x, reduce the exponent by 1, and the derivative of x squared is 2x. And now I want to find the critical numbers of this, so I'm going to set it equal to 0 and solve. I started by taking this power of x and moving it down to the denominator down here to make the exponent positive. That might make the solving a bit easier. I'll now take this term, move it to the other side, making it positive. Then I'll multiply this x squared to the other side. 2x times x squared would be 2x cubed. I'll now divide the 2 to the other side, giving me x cubed is equal to 216. And then to isolate the x, I'll raise both sides to the power of 1/3, giving me x equal to 6. So what I've just figured out is that when x is 6, the rate of change of the surface area is 0, meaning it might be a minimum, might be a max, might be neither. We should verify with a derivative test that it's in fact a minimum value for the surface area function. So I could do a quick first derivative test or second derivative test, but I think I'll pick first derivative test and check the rate of change, so the value of the first derivative on either side of 6 to see if it goes from negative to positive, verifying it would be a min point. So I'll set up a chart. Now, x has to be bigger than 0, but it could be infinitely big, and the only critical number between 0 and infinity was 6. So let's check the sign of the first derivative in each of these intervals. Between 0 and 6, I'll pick a test value. I'll just pick 1, and then between 6 and infinity, I'll pick 10. I'll take each of those values, sub them into my first derivative, and see if I get a positive or negative answer. Subbing in 1, I get a negative answer. Subbing in 10, I get a positive answer, meaning the surface area is decreasing before 6 and then increasing after 6. So at 6, it was at a minimum surface area. So I can answer the question now. The dimensions that use the least amount of mesh are x equal to 6 and y equal to, well, to calculate y, I can use this relationship between x and y that we have in the constraint. If I sub 6 in for x into this equation, 144 over 6 squared, so 144 over 36 is 4. And now let's go on to the last question of the calculus part of the exam. This is the curve sketching question. It says use the algorithm for curve sketching to sketch the graph of this f of x polynomial function. Part 1 of the algorithm says state any asymptotes or holes in the graph. Well, this is a polynomial function, so it doesn't have any asymptotes or holes. To find the x-intercepts, I'll need to set the function equal to 0 and solve for x. And to solve this equation, I'll start by common factoring out an x, and then that quadratic inside the second factor, it would factor further. The numbers that multiply to 9 and add to 6 are 3 and 3, so it would factor to x plus 3 times another x plus 3, which I'll just write as x plus 3 squared. And then that product would be 0 if either that factor was 0, which would happen if x was 0, or if this factor was 0, which would happen if x was negative 3. So my x-intercepts are at the points negative 3, 0, and 0, 0. And this point 0, 0 is right at the origin. So not only is it an x-intercept, but it's also the y-intercept. So I don't actually have to calculate anything for the y-intercept, but if I wanted to, I could verify my answer to find a y-intercept just by subbing an x for 0. So if I evaluate f at 0, if I replace each of these x's with 0 in the equation, it eliminates all of the terms, and I just get 0. So that verifies that the y-intercept is at the point 0, 0. The next step in the process is to find the critical points. So those are the points where the slope of this polynomial function would be 0. So I'll have to start by finding the derivative of this function, and just using the power rule, I could find the derivative of each term. The derivative of x cubed is 3x squared, plus the derivative of 6x squared is 12x, plus the derivative of 9x is 9. And now to find the critical numbers, I'll set this to 0 and solve. I'll common factor out a 3 from all of the terms, and then this quadratic is factorable. The numbers that multiply to 3 and add to 4 are 3 and 1. So this would factor to x plus 3 times x plus 1. And then the product of those factors would be 0 if any of the factors were 0. X plus 3 would be 0 if x was negative 3, and x plus 1 would be 0 if x was negative 1. So my critical numbers are x equals negative 3 and negative 1. It asks for the critical points, meaning I need the y values that go with each of those x values. So I'll find my critical points just by taking negative 3 and negative 1 and subbing them into the original f of x function right here and calculating the corresponding value of y. Well, when we sub in negative 3, we should get 0, right? Because that was an x-intercept on the function. And when subbing in negative 1 into this function for x, I would get negative 4. So the point negative 1, negative 4 is a critical point. The next step in the process is to find the possible points of inflection. To find the possible points of inflection of a polynomial function, I find the second derivative by differentiating the first derivative. So if I differentiate each of the terms, the derivative of 3x squared is 6x, the derivative of 12x is 12, and the derivative of 9 is 0. So there's my second derivative. At a possible point of inflection for a polynomial function, the second derivative will be 0. So I'll set it equal to 0 and solve for x. Solving for x in this equation, it's just a linear equation, so I can solve it just by rearranging and isolating x, and I would get x is equal to negative 2. So there's a possible point of inflection at negative 2, comma, I have to calculate the y by subbing that into the original function, and it actually gives me a y value of negative 2. So at this point, the function might change concavity. And at these 2 points, there might be a local max or local min. I have to check if there are local extrema or points of inflection by making a sign chart that uses those critical numbers and possible points of inflection as dividing points and will test within the intervals that they create. So what I've done is I've created a chart where at the top, I've created 4 different intervals using both the critical numbers and the possible point of inflection as the dividing points. And now within each interval that I've created, I want to record what is the sign of the first derivative and the second derivative so that I can see if the original function is either increasing or decreasing, concave up or down, so that I can classify any local extrema or points of inflection. Let's start with the first interval between negative infinity and negative 3. I need to pick a test value, so I'll pick any number in that interval. I'll pick negative 10. I'll sub it into both the first derivative and the second derivative and record the sign of the answer. If I were to sub negative 10 into the first derivative, I'll get a positive answer. Into the second derivative, though, I'll get a negative answer. The fact that the first derivative is positive tells me the original function is increasing, and the second derivative being negative tells me the original function must be concave down. Increasing and concave down means it makes that shape. And then in the next interval from negative 3 to negative 2, I'll pick a test value of negative 2.5, sub that into both the first and second derivative. Subbing it into the first derivative, I get a negative answer, and into the second derivative, I get a negative answer as well. Because the first derivative is negative, I know the original function is decreasing, and the second derivative being negative tells me that it's concave down. Next interval between negative 2 and negative 1, I'll pick a test value of negative 1.5, subbing that into both the first and second derivative. Into the first, I'll get negative. Into the second, I'll get positive, which means decreasing and concave up. And then the last interval from negative 1 to infinity, I'll pick a test value of 0. Into the first derivative, I would get a positive answer. Into the second derivative, a positive answer, which means it's increasing and concave up. Now you can imagine if you were to connect all of these pieces together into one continuous curve, that's going to be the shape of f of x. Let's also record if we had any local maxes or mins or any points of inflection. At the critical numbers, there might be a max or min if there's a change in the sign of the first derivative. At negative 3, the first derivative changed from positive to negative, so it went from increasing to decreasing, meaning it was a local max. And at negative 1, the first derivative went from negative to positive, meaning the function went from decreasing to increasing, so there was a local min at the point negative 1, negative 4. And then at an x value of negative 2, it was a possible point of inflection. So we have to check, did the second derivative change signs? Yes, it went from negative to positive, meaning the function went from concave down to concave up. So there's a change in concavity, meaning at the point negative 2, there is a point of inflection. And now we can do an accurate sketch of the curve of f of x using all of this information. So there's the end of the calculus part of the exam.